It's the last day, but it's actually going to be an incredible day with some really awesome talks. So I thank you all for being here this morning. I'll come back to some more things later. Our final keynote speaker is Professor Ayfer Ozgur from Stanford University. We've kept it a little informal, so I'm not going to read a bio, but she's amazing, and you'll find out from her talk.
Thank you. Thank you so much, Lita. And thank you so much for the invitation to speak here.
I mean, she's an incredible role model, but what could be better than having a really awesome 8-year-old in the audience? That's called really juggling work-life balance.
Okay, so very happy to be here. So in this talk, I would like to tell you about this notion of information constraint optimal transport. And this is a story about how this notion emerged when we were studying. We were looking at some very classical fundamental problems in information theory, like the capacity of the relay channel, and then how it took us all the way to privacy in generative adversarial networks. And so I've been working on this topic on and off for quite a while now. So I'll try to summarize the main ideas from a few of our papers. And these are joint work with different subsets of the people you see here. So Daria Reshetova and Wenning Chen are my PhD students from Stanford. Wenning is here. And Yukin Bai and Xiugang Wu are from the University of Delaware. And what we'll try to do in this talk is to see how this notion of information constraint optimal transport relates to a couple of things here. The first thing will be the work of the French mathematician Talagrand, his work on transportation cost inequalities. And then we'll see how it relates to the work of the famous information theorist, Katalin Martin. So her claim to fame is to establish this connection between transportation cost inequalities and concentration of measure. And then we'll see how this notion emerges in the study of this relay channel in a problem that's formulated by Tom Cover. And finally, I'll tell you how this notion becomes useful in the context of generative adversarial networks. And roughly, I guess the plan is to spend the first half of the talk on these first three topics, and then the second half on this last topic. Okay. Okay, so to tell you about information constraint optimal transport, I first need to tell you about optimal transport. And this is a problem that goes a long way back to the French mathematician Monge, 1781. His note on land excavation and infill, where he formulates the following problem. So he says, let's say we want to excavate some land here of some prescribed shape px. And then we want to take the land we excavate and transform it to this target shape py. And mass will be preserved here. So without loss of generality, we can assume that the total mass is normalized to 1. So you can think of these shapes as defining just probability distributions. So now our problem can be stated as follows. So let's say we have a random variable x with this distribution px. And then we would like to find a mapping that will transform this random variable x to this target random variable y with this target distribution py. So both px and py are given to us. And among all such mappings that transform x to y, we would like to find the one that minimizes the expected value of a given cost function. And the cost function captures the cost of taking 1 unit of mass from this point x and carrying to this point y. So in Monge's problem, this can simply be the distance between these 2 points. Okay, and you can think of the expectation here as carried over the joint distribution of these random variables. So note that in the beginning, we start with just 2 marginal distributions, px and py. But once you fix the coupling between them, the mapping, this defines a joint distribution for x and y with these marginals. And then we are basically trying to find the best coupling here that minimizes this expected cost. And this problem gets rediscovered some, I guess, 160 years later by the Russian mathematician and economist Kantorovich during the World War II. I guess at the time they need to deal with a lot of logistical problems. They need to carry soldiers and goods between different places. So he reformulates the problem, and he actually introduces a small but important generalization in the formulation. So in Monge formulation, this mapping has to be deterministic. And that actually makes the problem ill-defined in some cases. For example, if you have just a one point mass here, so if the source distribution is just a point mass, and you restrict the mapping to be deterministic, then you can't create a shape like this, because a deterministic function cannot take one point x and map it to the two different points. So you cannot split mass with deterministic mappings. And Kantorovich allows this mapping to be randomized, in which case you can think of it just as a conditional probability distribution, or a channel in the information-theoretic language, a channel that takes the input distribution px and transforms it to this output distribution py. And once you fix that channel, right, this defines a joint distribution for x and y with these prescribed marginals. And again, among all such joint distributions with these given marginals, we would like to find the one that minimizes the expected value of a given cost function. Okay, and this turns out to be a very fruitful area in mathematics that sees a lot of famous names, a lot of famous awards. So Kantorovich gets the Nobel Prize in 1975 for his work in this area, together with Koopmans. And then Danzig invents linear programming in this context, because if you go back, this problem is actually a linear optimization problem, because both the objective here and these constraints, they are linear in this joint distribution P. And it's an area that has found a lot of applications also in many different areas, from economics to meteorology, and most recently in machine learning. And in the second half of the talk, I'll try to tell you about some of these applications in machine learning. Okay, so for most of this talk, we will fix the cost function to be a specific cost function, and that would be the squared Euclidean distance between the 2 points. And that turns out to be a natural cost function for a lot of applications. And if you do that, if you fix the cost function to be this one, and then you take the square root of this optimal cost, then this resultant quantity actually has a name of its own. It's called the quadratic Wasserstein distance. And one can actually check that it defines a proper distance metric between distributions. So intuitively, right, if you have two distributions that are very similar to each other, then the cost of transporting one to the other will be small, right? And if they are very different, the cost of transporting one to the other will be large. So you can use this quantity to measure, to define a notion of distance and measure similarity, dissimilarity between distributions. And one research line that has been of significant interest in mathematics is the development of so-called transportation cost inequalities that bound this quantity here. So this is a famous one by Talagrand from 1996, which says the following. So now, if you take one of these distributions here to be the Gaussian distribution with zero mean and identity covariance matrix, then this inequality says that the squared Wasserstein distance between this Gaussian distribution and any other distribution is always bounded by 2 times the KL divergence between these two distributions. Okay, and I guess one way to interpret this inequality would be that, okay, we can use Wasserstein distance to measure similarity between distributions. KL divergence is another measure for measuring similarity, dissimilarity between distributions. So this inequality says that this measure is always bounded by 2 times this measure. But the reason why these transportation cost inequalities have been of significant interest in mathematics is because people have shown that, for example, transportation cost inequalities of this form can be used to measure concentration results. And this is actually the major contribution of Catalin Martin to establish that connection from transportation cost inequalities to concentration results, which roughly say that if you have a nice smooth function that depends on a lot of independent random variables, then this function will concentrate around its mean exponentially fast. And indeed, the transportation cost inequality from the previous slide can be used to prove this Gaussian measure concentration result. And then people have also shown that these kind of results are also essentially equivalent. They capture the same phenomena as so-called isoperimetric inequalities in geometry, which at first seem completely unrelated. So what are isoperimetric inequalities? I'm sure everyone is familiar with the isoperimetric inequality on the plane, at least at an intuitive level, right? Which says that if you draw shapes on the plane, two-dimensional shapes like this, with the same perimeter, isoperimetric means same perimeter, then the circle will be the one that maximizes its area for a given perimeter. And actually, that transportation cost inequality from the previous slide can be shown to be essentially equivalent to an isoperimetric inequality in Gaussian space, meaning that when the measure in the space is given by the Gaussian distribution. Okay, so there are some interesting set of connections here between kind of problems that at first seem quite not that related to each other. Okay, so any questions so far? This was more or less the background on optimal transport. So what I would like to do next is to define the quantity that will be our main focus in this talk, which will be a variation of this notion of optimal transport or Wasserstein distance. And we'll call it information constraint optimal transport. Okay, so what is this quantity? So remember, in the definition of the Wasserstein distance, right, we have this optimization over all possible joint distributions with these prescribed marginals, right? So what we would want to do now is we would want to constrain these joint distributions by saying that the mutual information this joint distribution induces between X and Y cannot exceed a given threshold. So in this optimization, we only consider joint distributions that induce a bounded mutual information between X and Y, so smaller than a given threshold. We'll call that information constraint Wasserstein divergence now, because technically speaking, it's not a distance metric once you introduce this constraint.
I suppose you could view it as passing through a specific family of channels. Like... Yes, exactly. So what this constraint does is, remember in the beginning, I told you that in Moore's formulation, the mapping had to be deterministic, right? And then we said Kantarovich relaxed it to allow for randomized mappings, right? But it turns out that in a lot of interesting non-degenerate cases, even though you allow for randomized mappings, the optimal mapping still turns out to be deterministic. And in some cases, you may want to enforce some amount of noise randomization in that mapping. And this is exactly what this mutual information constraint does, right? Because if the mapping between X and Y is deterministic, X is a function of Y, then this mutual information here can be potentially very large, even unbounded in the continuous case. And what this constraint does is basically it limits that mutual information. And by basically controlling this R, you can control how much randomization you want in this mapping. In the limit, I guess, if you take R to be 0, then the mutual information has to be 0. This means that the only coupling you allow here, joint distribution, is the independent one, okay? And we'll see some other reasons why one may want to look at this quantity, but this is what the constraint does. Okay, and the first thing we'll do is we'll show basically an upper bound on this now information constraint Wasserstein divergence that has a similar flavor to Talagrand's inequality.
in the sense that we fix one of the marginals here to be a Gaussian distribution. And we say that the squared information constraint Wasserstein divergence between this Gaussian and any other distribution has to be bounded by this right-hand side, which is now more complicated. So it depends on two parameters related to this X distribution, the second moment and the entropy. And it also depends on the R, the amount of the constraint on the mutual information. Okay, so why is this interesting? Well, I guess the first thing you can do here, you can, as a sanity check, you can take R to infinity. And when you take R to infinity, you are essentially removing this constraint. So this quantity just reduces to standard Wasserstein distance. And then you can see what you get on the right-hand side and compare it to the right-hand side of Talagrand's inequality. And if you do that, basically this is what you get. And you can prove that this inequality is always tighter than Talagrand's inequality. And actually, it's achieved with equality for a slightly wider class of distributions as compared to Talagrand's inequality. But I think more interestingly, it turns out that this inequality also has a natural counterpart in this isoperimetric world. It turns out that this one captures the isoperimetric inequality on the sphere, which says that if you live now on the surface of an n-dimensional sphere and you ask the same question among all sets on the surface of the sphere with the same perimeter, with the same neighborhood on the sphere, what is the one that maximizes its measure, its area? It turns out to be the spherical cap. So that's the isoperimetric inequality on the sphere. And what you see there is in its heart saying the same thing as this isoperimetric inequality. Okay, and turns out that the more general version with the mutual information constraint, that also has a natural kind of counterpart as an isoperimetric inequality, and it corresponds to some strengthening of this isoperimetric inequality on the sphere. Okay. And okay, all this for us really started when we were looking at this problem. So this classical problem in information theory, the capacity of the relay channel. We were intrigued by a version of this problem that was formulated by Tom Cover in this book, Open Problems in Communication and Computation in the 80s. And then at some point, we were able to solve this problem. But then the first proof we came up with was quite complicated and long. And we always felt like for a year after that, we felt like there must be a more direct way to make the same argument. And I guess if you stare at something for long enough, then it comes to you. At some point, we realized that what that long proof was really doing was proving that transportation cost inequality on that information constraint, Wasserstein divergence. And once you have that inequality, then you can actually prove the result for this problem just in a couple of lines. And I guess this is for people who have looked at these kind of problems in information theory. So the way we use this inequality is at a very high level, right? So we are actually trying to prove a converse for the capacity of the relay channel. And when you prove a converse, you always start with this Fanow's inequality to say that the block length times the capacity is smaller than the mutual information between the inputs to your channel and the outputs collected by the destination. And in this relay channel problem, there are two of them, one from the direct link and one from the relay. And then what we do is, so there are some n-dimensional variables, right, associated with this problem. And what we do is we take certain marginals associated with this problem, and then we couple them. So basically, we are creating, if you like, a new set of random variables where certain marginals are preserved, but certain marginals are coupled with each other. They have dependence now. And then we bound this mutual information in that new kind of setting that we create where things are coupled with each other. But because certain marginals are preserved, this mutual information is preserved. And I guess in that new setting, bounding this becomes immediate with this inequality. Okay, so this is a very high level idea if it makes any sense to people. Okay, so, and once we finished this work, I was really excited because I felt like this quantity, not just, because it emerged in this relay channel, but in itself, I thought it was a very natural thing to study, information constraint, Wasserstein divergence. And I guess it turns out that if something is very natural, then it's very likely that it also showed up in other people's work. So I think I read this in a paper by Jack Wolf. He said something like, every new good idea is a reincarnation of an old good idea. And this was certainly the case here. So it turns out that this quantity, we realized, can be traced back all the way to Schrödinger, 1931. And this was even before Kantarovich formulated the optimal transport problem. This is even before the axioms of probability were there. And obviously, he didn't state his problem in these terms exactly, but if you look at the heart of what he was doing, it was related to this notion here. And then we also realized that this quantity, actually in this Lagrangian form, right? So this is a constraint optimization problem here, and you can take this constraint and you can make it part of your objective here by introducing a Lagrange multiplier. And this version has been of significant interest in the recent machine learning literature. And it goes under the name entropy regularized optimal transport, entropic Wasserstein distance, Sinkhorn divergence, and so on. I guess I'll just call it information constraint Wasserstein divergence for consistency throughout this talk. But the reason why people in the machine learning literature have been interested in this notion is mainly for computational reasons. Because they want to compute the regular Wasserstein distance without this mutual information. But without the mutual information, computing the Wasserstein distance involves solving this optimization problem, right? Overall couplings here, overall joint distributions. And that optimization problem turns out to be computationally prohibitive for many. It's a linear program, but the computational complexity is still high for many of the problems we would like to solve in practice. So instead, they introduce this mutual information, and that this makes the optimization problem strongly convex. And then you can then solve it much more efficiently, compute this one much more efficiently than the original one. So you basically just compute this one and then take it as a proxy for the true Wasserstein distance. Okay, and obviously this computational aspect is very important, but I guess for me as an information theorist, it's more interesting to think about what adding this mutual information to your problem now does to your solutions, right? And in the rest of the talk, I'll try to tell you a little bit about that in the specific context of generative adversarial networks, because this is one area where this Wasserstein distance has proven quite useful. Okay, so what are generative adversarial networks? So these are a popular method today for learning distributions from data by modeling your target distribution as a function of a known distribution. Okay, so you're trying to learn a mapping here, which is called the generator, and it's usually represented by a neural network. And you want this generator, this mapping, to be able to take samples from this known distribution and transform them to samples from this target distribution. And you can formulate this as an optimization problem by fixing basically a loss function here, and a way to measure the distance between your generated distribution at the output of the generator and the target distribution. And one popular metric for that is the Wasserstein distance. And then you basically have to solve this optimization problem here. You have to find the best mapping, the best generator in a given class that minimizes the Wasserstein distance between the generated distribution at the output and the target distribution Py. But a lot of times you won't know what the target distribution is. You just have samples from that target distribution. So this target distribution here will have to be replaced by the empirical distribution of your n samples. So instead of solving the previous problem, you solve this one here with the empirical distribution. And GANs have been obviously very successful. They have demonstrated impressive results in a lot of different domains. But they also have a number of issues, like they are slow, they suffer from slow convergence, they suffer from stability issues. And one difficulty is that it's sometimes difficult to quantitatively evaluate the performance of a generator you learn, because you don't know what the optimal solution is. So it's difficult to say how close you are to an optimal solution. And to get some insight on some of these problems, there was a paper by one of my colleagues' groups, David Che at Stanford, and his students a couple of years ago, where they proposed to evaluate GANs on a very simple benchmark. So this is the Gaussian linear setting, a very simple setting where this input distribution here is Gaussian, zero mean identity covariance metric, dimension R small. And then the target distribution here is also Gaussian, zero mean, let's say covariance KY, and the dimension D is now larger than R. And the generator is restricted to be linear, okay, in which case you can think of it just as a matrix that takes samples of dimension R and maps them to samples of dimension D. And obviously, because the output is a linear transformation of this input, which is Gaussian, the output will also be Gaussian in this case, but it will be a degenerate Gaussian distribution because the covariance matrix can be at most of rank R, because the input is of dimension R. And the question is basically what G here will minimize the distance between the output distribution, the Gaussian you are able to generate, and the target Gaussian here. And it's not too difficult to show that the optimal G here will come from the RPCA solution of Y. So meaning that you will look at the R top eigenvalues of KY and the corresponding eigenvalues and eigenvectors. And then this G will have those same top R eigenvalues, and or I should say the covariance matrix of the distribution you create here will match this covariance matrix in the top R eigenvalues and eigenvectors. Okay, so in this simple setting, we know what the optimal G is, okay? If we know that the target distribution is Gaussian with this covariance matrix, we know that the optimal G star comes from this RPCA solution. But in practice, you can't solve this problem because you don't know the target distribution. Instead, you only have samples from this distribution. So instead, you need to solve this problem where the target distribution is replaced by the empirical distribution of the samples that come from the same distribution. We'll call this our empirical solution. We'll call that the population solution. And what they show in this paper is that even in this very simple linear Gaussian setting, the convergence of this Gn to G star will be very, very slow in the following sense. So if you look at your Wasserstein distance to the target distribution and the output of the empirical generator versus the Wasserstein distance between the target distribution and the generated distribution by the optimal generator. So ideally, right, if Gn is close to G star, you want these things to be the same, so the difference to converge to zero. And it does converge to zero, but very, very slowly with n, where n is the number of samples we have. So the exponent of n here is 2 to the d, where d is the dimension of the output. So this means that even if the dimension of the output is something like 20, the convergence here is very, very slow. So even in the simple setting, you need a lot of samples in order to converge to the optimal, to the true solution. And when this notion of information constraint, Wasserstein divergence, emerged in our work, the first thing we wanted to do is to basically see what will happen to the conclusions of this paper if we replace the Wasserstein distance now with this information regularized Wasserstein distance, Wasserstein divergence. And you can do that. So the problem is the same, just that now our loss function changed from the regular Wasserstein distance to this information regularized Wasserstein distance. And here you can show a couple of things. You can first show that in this Gaussian linear setting, you can again characterize the optimal solution. And indeed, we see that when you add the mutual information, the optimal solution changes. So regularizing with the mutual information actually changes the generator you learn. And the generator you learn is now a kind of soft thresholded RPCA, meaning that you'll take the top R eigenvalues of that target covariance matrix, but you would actually eliminate some of them that are smaller than a given threshold. So you will further sparsify, you will further reduce the rank of your generated distribution. And then we can also show that if you do this, and not only for the Gaussian linear case, but when, as long as this Px and Py are sub-Gaussian, and the set of generators is either the set of linear generators or Lipschitz generators, you can basically show that with this mutual information regularization, now you'll get much faster convergence to the optimal generator here. So now the convergence here will be like 1 over square root of n. So we can get rid of that dependence in the exponent of n to the dimension d. We don't have an exponent anymore that decreases with the dimension. So regularizing with this mutual information can enable faster convergence. Any questions, by the way? I didn't stop for questions, but you're always welcome to ask.
The works by Ziv on the smooth Wasserstein distance just for the curse of dimensionality. Will that help here, or is it, how is it related?
I think so. I think so. Basically, our result, so usually, as far as I'm aware, the kind of results that Ziv is looking at is more about just the convergence of the Wasserstein distance between, if you take two empirical distributions, right, for Px and Py, and you study how fast the Wasserstein distance between the two empirical distributions converges to the Wasserstein distance between the two distributions. What we do here is we build on those kind of results, but there are extra steps that you need to take care of here, because this, in this case, Px and Py, the two distributions tend to be, they are actually correlated with each other because one is generated as a function of the other. So you have to handle that dependence. And also you want a result for the minimum for the best G, which doesn't, so basically I'm saying if there is a result like that, it's possible that you can work out a corresponding result for the GAN case. Yes, but we didn't try that specifically.
Yeah, so so the choice of mutual information, I understand the connection with the relay channel, but here in these, and I know Marco Couturi's work, and I know that these really nice, simple synchron optimal transfer algorithms. But the choice of mutual information is still a little bit arbitrary as regularization penalty. So have you explored other options as well, like some other F divergence instead of KL divergence?
I should say no. The other thing we explored was you can take a version of this mutual information regularization. Basically, you can, because this is biasing the solution, and you can debias it. But it's still regularizing by mutual information, basically, and then you can basically have your loss function recover the RPCA solution exactly. But we didn't try other F divergences. Yeah, that would be interesting. I guess for me it was really like there was this quantity that emerged, and I was really excited about it, and I wanted to understand what else this can be useful for. And this is one thing that it can be useful for, but obviously it's possible that you can get similar kind of results with other loss functions here too.
Maximo's question, then I'll ask a question later.
All right, but first of all, to make a comment, it was really funny when you mentioned Ziv. My first thought was Jacob Ziv because I'm old, and now you're doing on Ziv old.
That's right. Somebody should have
like, wait, Ziv
that.
did this anyway. But I just wanted to also point out the work of Saldi, Linder, and Yüksel on this information, what they call information lossy source coding with constrained alpha distribution, where they considered minimizing expected distortion between X and Y, subject to marginal constraints on X and on Y, and mutual information between X and Y. And so they actually had very interesting connections, kind of a structural result for these things, where they said you can actually use optimal transport as a building block of these codes.
That's
direct,
I should have mentioned that. So this information constraint, I guess, this information constraint Wasserstein divergence also emerges in that context of source coding. And I feel even Bob Gray has some earlier papers on that that go along with that.
It was Jim O'Mora and O'Mora and it was just O'Mora and Gray.
So I want to make one more comment. That was actually a great question because at least in the GAN literature, that kind of, I have only empirical distributions, I have only 2 distributions. It's broadly called generalization by Aurora and others. And this is sort of called estimation by Liang and others. It's just a weird terminology to differentiate the 2 quantities.
I guess I'll call it excess risk to me. Because it's basically
Daria convinced me that's what she's calling it.
Because this is the minimum risk you can have for this problem, right? And this is the difference is the excess risk you have to tolerate because you weren't able to solve the population problem and you were only able to solve the empirical problem.
But this is also unrealistic because you never have the ground truth PY in any case. So generalization is really the right metric in the sense that how good does your learning algorithm do relative to the statistical ground truth? So in that sense,
I agree. I mean, in practice, when you don't know this may be difficult to compute. But I guess the theoretical result is saying that whatever that is, you are guaranteed to converge to that optimal, basically with this rate here, with this parametric rate.
Yeah, but you're assuming PY is known. PY is the real samples whose distribution you don't really know.
No, this is in the following sense, right? So I'm not assuming PY is known. I'm just saying that whatever PY is, right, as long as I know it satisfies the assumptions of the theorem, then I know that the optimal, the excess risk will decrease to 0 as 1/√n. I mean, I may not be able to compute this excess risk because I don't know this G star in practice, right? But I'm ensured that in this setting, I will converge, my excess risk will go to 0 as 1/√n. Okay, and I guess in the remaining part, hopefully I had some, do I had some 10 minutes or so? I think I do. Okay.
You do.
Okay.
15 easy.
Okay. Then in this last part, I'll try to give you one more application for this information constraint Wasserstein divergence. Again, in the context of Wasserstein GANs. And this is actually a simulation here. I guess before we go into that, so this is just to validate the theoretical results here. And these are experiments with the Gaussian distribution again, because in practice, in order to compute your distance to the optimal solution, you have to know what the optimal solution is. So that's why we chose to work with in the Gaussian setting here. And you see that, so this blue and green lines, they correspond to GANs trained with, the loss function is the standard Wasserstein distance. And for this orange and red one here, the loss is the information regularized Wasserstein divergence. And you see that you converge to the optimal distribution, to the optimal generator much faster with the regularization as the theory suggests. And in some cases with the standard Wasserstein distance, actually you have you can be far away from optimality. Okay, so the next thing is basically how we can use this for privacy in GANs. Okay, so a lot of times when we want to learn a generative model for our data, the data may contain private and sensitive information. So maybe these are images that users take with their mobile phones, right? And they may not want to share their personal images with the world just as they are with the learner or the data curator. And one possible solution in this case can be to do the following. You can take the samples generated at the users, and you can first pass them through a local privatization mechanism here, M, and you share with the world, with the learner, only the output of this privatization mechanism, only the privatized sample, YI. And hopefully this privatization is done in a way such that this YI doesn't reveal too much information about the raw sample UI. I won't define formally what the notion of local differential privacy is, but you can just think of it as adding some sufficient amount of noise to the sample so that you are hiding the raw sample. So for example, if our samples here are images from this MNIST dataset, instead of sharing these samples as they are, you're sharing this, which is the kind of noisy version of this. So noise added so that you're hiding the underlying information. And the question we would like to ask in this case is, how can we train GANs from privatized samples, from these YIs? And indeed, we face an immediate challenge here, because if you take the GAN formulation from the previous slide, remember, we want to find a generator from a given class that minimizes the Wasserstein distance between the generated distribution and the empirical distribution of our samples. So in this case, we only have privatized samples. So if I use privatized samples, if I replace this with the empirical distribution of the privatized samples, then I'll be training a generator that generates the privatized samples, the noisy samples, and not the original samples, right? So then the question is, how can I modify this framework so that I encourage my generator to generate the raw data distribution rather than the privatized data distribution? And I guess, as you can guess at this point in the talk, the solution turns out to be regularized with mutual information, okay? So if you change your loss function here, the Wasserstein distance, from the regular Wasserstein distance to the information regularized Wasserstein distance, and you adjust the regularization parameter correctly, then this generator will actually generate the raw data distribution, even if you plug in the privatized samples here. And this is essentially the main theorem here. So this holds when the privatization mechanism you use locally for privatizing the samples is an additive noise mechanism like Laplace or Gaussian. And in this case, we are actually not just interested in the quadratic Wasserstein distance, but we are interested in P Wasserstein distance more generally. So the difference now is that this cost function that we hit here is not just the squared Euclidean distance, but it's the P norm raised to the power P. This is the P Wasserstein distance. And turns out that in order to get rid of that privatization noise, in order to encourage the output of your generator to generate the raw data distribution, you need to adjust, you need to choose the P here according to the tail decay of your noise distribution. So maybe it's just easier to go over the two corollaries I had here.
I'm going to ask you a question. Go back to, so somehow it feels like violating DP if you do this. The whole idea of synthetic data for the DP guarantees is to say that you could actually inevitably release a row of the data set through any kind of generative model. So this is why I add noise. I mean, this is a great question. I still want to be sampling from the original distribution, but is there a way to guarantee that the learned model is still differentially private.
Yeah, the catch is that I'm not saying you'll be able to recover the original samples.
Yeah,
I'm just saying you will learn the distribution from which these samples are coming from, and you'll be able to sample from that distribution.
Yeah, but in a discrete setting, that could reveal, if you know the support, then you very much may have sampled from the data set in that.
I mean, the local differential, so this mechanism has to satisfy formal local differential privacy guarantees, epsilon or epsilon delta, whatever you like. And once you have that, I mean, those guarantees hold for everything that follows, right? And I mean, that can't be violated if it was if it was privatized, then it's privatized. But I think the catch is that I'm not saying you're actually learning these samples without noise. I'm not saying, actually, I'll show you examples. I'm not saying you can take this YI and you can recreate this UI. For example, this can be a face image, and this can be your noisy face image. I'm not saying I will be able to recover your photo. I'm just saying I'll be able to learn a noiseless distribution for generating human faces. At least theoretically, okay? So, and I'll show you some results. There are some limitations in the results, but I'll talk about that. Okay, so this is what it's saying. So here are the two corollaries that I'd like to mention. So if you're using the Laplace mechanism as your privatization mechanism, in this case, you should use the one Wasserstein distance with information regularization here. And the regularization parameter, that lambda, has to be chosen to match the noise scale of this Laplace mechanism. And this theorem guarantees that if you were to plug in the target distribution here, this is the privatized distribution of the samples. This is the distribution from which the privatized samples are generated. But if you find the best G here, the output of that best G, the generated distribution, will actually be equal to the row distribution of the samples. So at the output of your generator, you won't be generating the privatized distribution, but you'll be generating the row distribution. This is what I'm saying. And again, in the case with the Gaussian mechanism, now in this case, P is equal to 2, so you should use the quadratic Wasserstein distance with, again, information regularization, and this regularization parameter has to match this noise scale. And same thing, if you plug in here the privatized distribution, what you will generate at the output of the optimal generator will be the true distribution, the row distribution of the samples. I see Lalita is not fully convinced, but we'll talk about it.
I think when you add Laplace and Gaussian mechanisms, irrespective of whether the input is discrete or not, the output is discrete or continuous. But suppose my discrete data was just 2 points.
If you did, you would have to do randomized response, in which case you'll get your support question is taken care of by the
yes. Yes.
Yeah.
So every sample now has a chance to take on every value because it has to because it's epsilon.
Yeah. Right. So what I'm saying is then the support is no longer the original support.
Yeah. Yeah. Well,
the randomized response
has to have full, every sample can have full support. Is what you're saying. Every noisy sample can have full support.
We'll talk about it later.
Okay, let's talk
it's
about
great
this.
to have.
Yes. Okay. Perfect. Okay. And okay. So this is assuming I have access to this privatized distribution. So I know the distribution from which my privatized samples are coming from. But again, just like we said before, in practice, I don't get to solve this problem. I get to solve this problem where I have the empirical distribution of the privatized samples. Okay, and what we can show in this case is a similar kind of convergence result. Like in the previous case, we can show that this empirical solution GN converges to the optimal solution G star, which generates the row data distribution. Again, in the sense that this difference here will converge to 0 as 1 over square root of n. And now the variance of the noise comes here, which means that if you want to add more noise, this means the convergence will be slower. So you'll have to compensate by using more samples here to achieve the same approximation here. Okay, and here are some experiments. Okay, so here we are using MNIST. So these are our original images, samples. These are the privatized samples. And actually, in order to, we wanted to see whether these privatized samples can reveal any information about the underlying original sample. So here, what we did was we did wavelet denoising for these noisy images. And we were actually generous to wavelet denoising because when we were choosing the parameters of the wavelet transform, you use the original images, which violates the privacy. And basically, you see that even if you do the optimal denoising, this noise is so much that you don't recover, at least in this context, we think you don't recover anything useful about the individual images. And here we try a couple of things. First, we train a regular GAN with the regular Wasserstein distance as our loss function. And we feed to this GAN these privatized samples. And you see that with the regular Wasserstein distance, you don't learn anything useful. These are samples from the output that are complete kind of garbage. The other thing we tried is we took these denoised images and we fed these denoised images to this regular Wasserstein GAN with the Wasserstein distance as the loss function. And again, you can't get anything useful. But if you feed this privatized images to now the Wasserstein GAN with information regularization, information regularized, you see that the output is not perfect, but you do generate something that's useful. Okay, so this is just to kind of validate the claim that regularizing with this mutual information does indeed inherently denoise the output distribution, and you are creating basically you're generating samples, or you're converging to generating samples from the original distribution. Of course, not perfect. And the kind of epsilon deltas we are able to achieve here, so the epsilon and delta guarantees for this privatizations here. In the first row, we use the Gaussian mechanism, and the epsilon is 35. In the second row, it's the Laplace mechanism, and the epsilon is very large, 196. So the formal privacy guarantees are not where obviously we want them to be. But I think this is saying something more about these being this metric being appropriate for this context of images rather than, right? Because we typically aim epsilon around 10 or something at least. But I think you see here that I don't think there is any way you can recover the original images, but because of the dimensionality of the sample, the kind of epsilons you can guarantee formally are quite large. And if you go for lower epsilons, so here, basically in this first row, we are using the Laplace mechanism, again with information regularized 1 Wasserstein distance. And the epsilon is 35 here and 25 here. And here in the second row, we use the Gaussian mechanism. Now with, again, the loss function is information regularized, now quadratic Wasserstein divergence. And the epsilons here are 30 here and 25 here. If you go lower, then you basically don't, the quality degrades significantly. And we think one of the reasons is that the MNIST data set is pretty small. So maybe the number of samples we have are not enough to compensate for the amount of noise we add, because our theory suggests that if you add more noise, then you'll need more samples to be able to converge. So we're still working on experiments. So I mean, we brought part of this, but part of this is still going on. Okay, so this was a proof for why adding mutual information denoises the output, but I think it's a little late for that, so I'll just skip. And I'll just conclude by saying that So in this talk, we talked about this notion of information constraint optimal transport. I talked about a transportation cost inequality for bounding this quantity. We talked about connections to isoperimetric results, how it comes up in the solution of Cover's problem. And finally, we talked about how this information constraint can be useful in achieving faster convergence in GANs, and also in the last part, achieving local differential privacy. And this was based on these 3 papers here. So yeah, thank you. And I'm happy to answer.
We have time for a couple of questions. Yeah.
So in the book on convergence with privacy, do you need to make any assumptions on the PU distribution?
Well, PY has to be sub-Gaussian, so therefore, I guess, yeah, I mean, this is the formal assumption. The PY, meaning the privatized samples that go here, this distribution has to be a sub-Gaussian distribution.
This holds for both the Gaussian, or
actually, the thing is that we have this convergence result only for the W2 case. So this is only for the Gaussian case. We don't have a corresponding convergence result like this in the case of W1. We think it may be doable, but we don't have it at this point.
Thank you for the very nice talk. Like, I was wondering if you could comment on the role of dimensionality also in the constant KFT, because, for example, in this data set, it is fairly high dimensional, like 700 dimensions, 784 dimensions. So, yeah.
This KD, right?
Yeah.
This is actually exponential in D. Yeah, this constant is exponential in D. It's always exponential in D in all these results. Yeah, I mean, it seems like exponential in D would be difficult to handle in practice, but these things still seem to converge. The other thing is that when you converge to something, right, and when you generate some samples, so this is basically saying that this says something about how close this generated distribution is to the true distribution, right? It doesn't say basically this generated distribution will not be close to the empirical distribution of the samples. So in practice, it may look like you're converging to something, right? But what you generate may be just the empirical distribution or something very close to the empirical distribution of the samples. You may be memorizing those samples and just regenerating them, right? So basically, in practice, I guess it seems like we are generating something, but again, we don't know exactly what we are generating, right? And this is a guarantee about how close you get to the true distribution.
Thanks.
there is another, I'm going to ask you a question. Broadly in the GANs literature, do you have a sense of what is a good measure? Scam likely is my best, a secret admirer. But broadly in the GANs literature, do you know what's, I mean, why Wasserstein? I mean, it's an IPM, it's easy to work with, but
W2
why not something else?
W2 is not an IPM.
W1 is IO.
W1 is.
Yeah.
I mean, well, I'm advocating the information regularized Wasserstein distance here. It also has dual forms similar to the Wasserstein distance. And actually one advantage is that in the dual form, you don't have constraints on the functions like Lipschitzness and convexity. So it may be easier to train in practice. I guess I don't have a good answer for that, but I'm here to advocate.
We all no, I mean, this is great. Yeah, not most of us do it, so I had to ask you.
Okay, perfect.
But it was a great talk. Thank you so much.
Thank you.
30-minute break and we'll be back.